Hey everyone, welcome back to another MCAT Shemmassian workshop. Today we're exploring a high-yield Chem Phys MCAT passage pertaining to carbon dioxide separation with quinone chemistry. We'll read the passage paragraph by paragraph, discuss any figures, and then we'll get to all of the questions, complete with explanations. Let's get started. And before we jump right into the passage, I just want to say that you can find over 4,000 MCAT practice questions on our MCAT question bank. But today we're just going to be going over a couple of them. So let's jump into the very first paragraph. The very first paragraph states that carbon capture is essential for mitigating carbon dioxide emissions. Compared to conventional chemical scrubbing, electrochemically mediated carbon capture, utilizing redox active sorbents, such as quinones, has been increasingly studied by researchers. However, the practicality of such systems is hindered by the requirement of toxic, flammable organic electrolytes or costly ionic liquids. And so, with this paragraph, there's a couple of key things that I would want to highlight. The things that I want to highlight would be carbon capture, mitigating emissions, electrochemically mediated, capture, redox active, and quinones. And the reason why I would highlight those things is because to me, I'm looking for things in passages that either are relevant to math or I call them miscellaneous facts. Things that would be found in the passage that almost sound like they would have content related to them, but it's up to me to identify that. Carbon capture, emissions, electrochemically mediated, redox active, quinones, right? These are things that we walk into the passage having an idea about, and they might be related to other concepts as well. So when I'm going through these passages, I'm focusing in on, again, on a couple of things. I want to organize things paragraph by paragraph. What makes this paragraph unique compared to other paragraphs? What am I likely to see in this paragraph that likely won't be in other paragraphs? But also, I want to be looking for things that have content rooted in them. And so I would be highlighting things so that I can navigate back to those if I was to get questions on them. Now let's jump into paragraph 2. It states that in a novel study, researchers tested whether rationally designed aqueous electrolytes with high salt concentrations could effectively resolve the incompatibility between aqueous environments and quinone electrochemistry for carbon capture. Reactive quinones can capture carbon as shown in figure 1, but they may also undergo undesired side reactions such as protonation or ion association. And then it states that figure 1, quinone mediated carbon capture, that is the title for figure 1. So again, let's jump into the highlights that we would do for paragraph 2. We might get that electrolytes with high salt concentrations, incompatibility, aqueous, and quinone. I might also get that reactive quinones in figure 1, undesirable side reactions, protonation or ion association. And this is going to be valuable because to me, this is something that I call a split in the passage. A split in the passage tells us it could either be A or it could be B. In this specific scenario, it gives us information about figure 1, which is always valuable, right? Sometimes you get questions about the figure, and the information comes from looking at the figure itself, but also sometimes questions refer to figures, but it's coming from the background or the summary or the setup of the figure information in the paragraph right before the figure. So I'm always wanting to pay attention to those things. And in this case, it tells us that figure 1 is pretty much showing us that this is how carbon capture can happen. But it also shows us that there's these side reactions that are undesirable, things that we don't want to happen. What are the things that we don't want to happen? Protonation and ion association. And so that would be about all I get for paragraph 2. So let's jump into figure 1 now. Again, the figure 1 title says that quinone mediated carbon capture. That's all it tells us. And in that paragraph right above, it's telling us that reactive quinones can capture carbon as shown in figure 1. And there's also these undesirable side reactions such as protonation and ion association. Looking at this figure, Just at first glance, it looks like a lot of information. It looks like almost too much information. And this would be a prime example of a figure that I just almost skate by. I spend about 5 seconds on it. I look at the figure title. I look at the information that should be in it. I look for key variables that will help me associate questions to this figure. So say a question asks me about protonation. Well, I know that protonation, say that there's multiple figures. I want to distinguish figures apart from each other. And so by me highlighting key variables, key terms, key differences in figures without going too detailed into them, it helps me go through the figures pretty quickly, but also locate which figure I should be referencing when I get to certain questions. Again, this passage right here only has one figure. So really what I'm looking for is a couple of things, right? In general, when I'm looking at figures, I'm looking for the figure title. I'm looking for the axes that will tell me the independent and dependent variables. I'm also looking for statistical significance and patterns. And so looking at this figure just at first glance again, it doesn't look like one of those graphs that would show me some type of significant value. It also doesn't look like it would show me any patterns. I see that there is a graph that shows us current versus potential, so I'll definitely pay attention to that. Those are some physics terms, and we know that in physics, anytime we start talking about terms like current, potential, there could be some math questions coming from that. So I would pay attention to that. I'd pay attention to, again, current, potential. Between the organic molecules that it's showing us, I really wouldn't pay much attention besides just kind of locking in my head that the compounds or the molecules, they're changing just slightly. As I go from A and I work my way down that graph, I see that there's a change in electrons and there's changes in carbon dioxide. I have a double bond O in that first part. That turns into an O minus in the second part. And then in that final reaction, I have some type of longer molecule. It's just a longer molecule, more oxygens, double bonds, and things like that. So I'm not trying to sit here and pay attention to every single little detail in all of these organic molecules. I'm just telling myself, there's an organic molecule, there was a double bond O, it changed, things changed on wherever that double bond O was. That's about it. I'm just looking at these molecules as before and after. I'm trying to keep it as simple as possible. And again, it does bring light to these terms called protonation and ion association. So I want to pay attention to those as well, because if a question references it, I at least know exactly where it's referring to. Now let's jump into paragraph 3. It states, the researchers measured quinone-mediated carbon capture in several different salt solutions, such as NaCl, KCl, Na2SO4, and NaH2PO4. In an experiment varying the NaCl concentration from 1 molarity to 10 molarity in increments of 1 molarity, researchers found a maximal rate of carbon capture at 6 molarity NaCl, after which a steep decline in carbon capture was observed. So again, things that I might want to highlight is that we're looking at carbon capture, salt solutions. It gives me a list of salt solutions, and usually when I get lists of things, I don't try to pay too much attention to it unless there's a very specific one thing on that list that continues to show up. In this case, it would be NaCl. We see that it goes in increments of 1 molarity from 1 molarity to 10 molarity. So I'd be highlighting those things. And I would also be highlighting that it has a maximal rate of carbon capture at 6 molarity of NaCl. Steep decline after. And again, like the things that are valuable here are almost like I'm just trying to pay attention to math type things, right? Like almost like a physics passage, like a hard physics passage. I'm getting a little bit of background about the experiment. We're looking at carbon capture with different salt solutions. One of those salts in an example is NaCl. We have range from 1 molarity to 10 molarity. We're going in increments of 1 molarity. and there's a maximal rate of carbon capture at this value, which is 6 molarity of NaCl. Afterwards, there's a decline. And so again, this is valuable because if there's a math question or there's a question asking me specifically about like NaCl or certain types of salt solutions, I know exactly what paragraph it's referring to. Again, we want to think about these paragraphs as reference points. What key terms are there? What kind of information is there? What kind of content is buried in there that's going to help me answer questions? And so this last paragraph was pretty heavy on that math. So that would be about it with this last paragraph. Before we jump into the questions, I just want to note again that if you're looking for more info on MCAT buzzwords, do check out our comprehensive list of high-yield key terms. They're going to be listed at the bottom of each content unit in our MCAT Premium Content Hub. Now, let's jump into those questions. All right, so let's jump into question number 1. It states, which of the following best explains the decrease in carbon capture after 6 molarity of NaCl? And so, right, we want to be thinking, where would this question be referring to? Hopefully you guys remember that we did talk about carbon capture. That's what this whole passage is about. And we did see 6 molarity of NaCl that did show up also in the passage, specifically in that last paragraph. And in that last paragraph, what do we know? It tells us that we're using these different salt solutions, and it gives us examples of those salt solutions. And again, NaCl being one of them. And that there's these NaCl concentrations, and we're bumping the concentrations up from 1 molarity to 10 molarity. We're doing it in increments of 1 molarity. And we found that the maximal rate is at 6 molarity of NaCl, but afterwards there's this steep decline. That's really all we know about this passage, right? Or like at least about this carbon capture using 6 molarity of NaCl. And so when we look at the answer options now, we're always looking for something I call similarities, pairs, differences, and extremes. Do we see any answer options that have similarities and pairs? Are there ones that are talking about the same topic, maybe different values, but same topic? Are there answer options that are a little bit extreme, that they say all or never or most? So we want to just kind of look at the answer options, get an idea. We know what the paragraph said about this information. It's a pretty general paragraph. We also now want to see the answer options and see which ones might kind of lead you into that right direction. And so answer option A says the solution became too acidic. Answer option B says the quinones associated with the ions first due to the high concentration of sodium. C says the high concentration of sodium sequestered the carbon instead of the quinones. So there's a high concentration of sodium. And D says the quinones were protonated quickly due to the high salt concentration. So what we'll see here is that answer option A has to do with acidity. Answer option B and C have to do with concentrations of sodium. And answer option D has to do with protonation happening quickly because of a salt concentration, which that kind of makes it so that there's about 3 answer options that have to do with a high salt concentration. And again, what do we know? We're increasing this salt solution of these several different salt solutions, which is NaCl. We have these different levels of salt solutions, and eventually we have a maximum capture rate. After that, there's this decline in carbon capture. And so likely the answer is going to have to be between B, C, and D, because those all have to do with this high salt concentration. Now, is it just having to do with the quinones associating with the ions first? Is it having to do with it being sequestered, the concentration of sodium sequestered the carbon instead of the quinones? Or is it having to do with protonation happening quickly because of the high salt concentration? So what we did there is we found the similarities between those answer options, B, C, and D all having something in common, high salt concentration. Now we looked at the differences. And so now we want to start chipping away. And so what we want to be thinking about is we have these quinones, we have these salt solutions. These salt solutions are using things like sodium. Those are metals. And so the quinones, they might be interacting with these metals and thereby decreasing their ability to sequester carbon. Because there's this steep decline in carbon capture at a high concentration of sodium chloride, it is likely that that sodium, those sodium ions, they're associating with that quinone and preventing it from carbon capturing. Because again, we want to think about it as you're adding this salt solution and it works great up until a certain point, but why would too much of it be a problem? Which is why the high salt concentration was important for B, C, and D, but it's probably again because the sodium ions, those are associating with that quinone and preventing it from carbon capturing. And so very likely the answer option is going to be B. We can also look at the other answer options and see that for A, the sodium chloride is not going to change the acidity of the solution, so that one's going to be out. When we look at C, it's going to say that, well, one thing that we want to think about is that the sodium binds to the quinone molecules, not the carbon. It just wouldn't make sense for it to attach to the carbon. And so C would be out. And then for D, sodium chloride, it doesn't protonate the quinone molecules because it doesn't introduce hydrogen ions into the solution. And so it can't protonate things. And so for that reason, D would be out. So again, B would be our answer for question number 1. So let's jump into question number 2. It states, the addition of a carboxyl group to a molecule is known as what? We have 4 different terms here, 4 different, keywords that this one's just going to be based off of content knowledge, right? You want to be thinking to yourself when you get certain questions, does this reference something in the passage? And if it does reference something in the passage, do I need it to answer the question? Or is this just straight content? And in this case, it would definitely be just straight up content knowledge. It's just asking you, if you were to add a carboxyl group to something, what would it be called? And you can see in the answer options, they picked all these terms that sound really similar because they're expecting students to get them confused, just because the names are so similar. And so for this one, it's just content. The addition of a carboxyl group is going to be a carboxylation. Therefore, answer option B is going to be correct again. Now let's jump on to question number 3. The question states, the researchers optimized the correct salt solution for their experiments, but they still measure a high amount of quinone protonation. Which of the following steps would most likely reduce the quinone protonation? So again, this is one of those questions where it's referencing something from the passage again. It's referencing that experiment. And you want to be thinking, is this something that's just straight up content knowledge, or is this something that I'd have to go back to the passage or the figure to answer? So some key things in this question would be that they are looking at the step that would reduce quinone protonation. How do you reduce quinone protonation? Again, we want to look at the answer options and look for similarities, pairs, and differences. We see that the answer options for A and B have to do with pH, and then the answer options with C and D are having to do with introducing some type of nucleophile or electrophile. So if that's the case, we want to think to ourselves, if we're trying to reduce protonation, would it have more to do with changing the pH or introducing some type of nucleophile or electrophile? Well, if we're trying to change the amount of protonation, it would probably have to do with pH, because pH just has to do with the amount of free hydrogen ions that are floating around. There's a lot of hydrogen ions floating around. Your pH is going to be really low. And so that would affect the amount of protonation. And so now thinking about this conceptually, as we're decreasing the pH, we have more hydrogens floating around. If we have more hydrogens floating around, the amount of protonation would increase as more protons would be available in that solution. So that being said, answer option B has to be incorrect. C and D, adding some type of nucleophile or electrophile wouldn't really affect the reaction of protonation, so C and D are out. And all that's left is going to be answer option A, which is if we increase that pH, the amount of protonation would decrease because there's going to be fewer protons that would be available to protonate that quinone molecule. So that being said, A is going to be correct for question number 3. Now let's jump into question number 4. And the question states, which of the following best describes the first forward step of the reaction shown in figure 1. And this is a great question because it references the figure for us. There's only one figure to refer to. It tells us exactly where in the passage we're going to be going back to. And so before we go back, I think it'd be valuable to just look at some of the answer options. If you do remember, when we were looking at that graph, we were saying like we don't want to pay too much attention to what's exactly happening in these organic molecules, but we did say we just wanted to pay attention to just like what's the big changes here. And if you recall, it was that double bond O that was starting to change as we went through those different steps. So if that's being said, right, well, what answer options would have to do with double bond O's changing? Looking at the answer options, there's only two that would be valuable for that, and it would be oxidation and reduction. Nucleation and combustion have nothing to do with oxygens either being protonated or being deprotonated or electrons being transferred. And so if that's the case, we're already going to be down to two answer options before we even go back to the figure, just based off of our simple observation before. But now if we were to go back to figure 1, what we would see is that in that first forward step of that reaction in figure 1, there's 2 electrons that are being added to the molecule. Well, if we're adding electrons, we're therefore having a negative charge, and that negative charge, that addition of electrons is known as a reduction. And so for that reason, our answer for question number 4 is going to be answer option D. Now let's jump into the 5th and final question. The question states, researchers measure a current of 13 microamps when potential is 0.2 volts on the CO2 curve. Assuming a circuit-like system with a single resistor, which of the following is the correct value for resistance? Now, this question is a classic physics math question that involves a couple of givens. It's got some values and numbers in there. And so keep in mind that in past passages, we've always stated that for Chem Phys, whenever you see math in the passage or math in the question, you always want to pay attention to it because you're likely going to be doing some equation math. Now, in this case, our givens are going to be 13 microamps and 0.2 volts, and that we're going to be solving for the variable for resistance. And so now what we should be doing is we want to look at the answer options again and look for some similarities, pairs, and differences and extremes. Again, like we're saying that like ideally, you know the math and you know the equation on how to solve these questions all the time. But what about the case where you forget the equation? Well, if that's the case, you want to have a backup plan. Like, can I at least narrow it down to 3 answer options or 2 answer options or even get the answer right? Just using a little bit of logic or similarities or pairs or differences. And in this case, what you'll see is that there are 3 answer options that are times 10 to the 4 or times 10 to the 3. They're in that range, right? So some pretty big numbers. So A, B, and C all have that in common. Answer option D is different because it's times 10 to the negative 5th microohms. So that's a really, 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 really small value. And so C is a pretty small value, but D is an incredibly small value. And so when you're doing this math, and when you're looking at this question, like in general, you just want to be thinking about, is it likely to be a bigger answer, like A or B? Or is it likely to be a much smaller answer, like C and D? And so considering we've got 13 microamps and 0.2 volts, when you're getting resistance values, it's pretty rare for you to have a very, very, very small value, like answer option D. And so if that's the case, I'm likely going to take that one out. Now I'm pretty much down to 3 different answer options, and between those 3, I have 2 pretty big numbers and 1 pretty small one. And that alone should kind of push me towards A and B, just because if I'm going to be doing and you also want to be thinking if you're a test maker, what numbers or what answer options would you want people to be picking between, or they would have a hard time without knowing the math? And in this case, it would be answer option A and B because they're pretty darn close. You've got 15 times 10 to the 3rd and 13 times 10 to the 3rd. And so with that being said, now we're going to have to actually go in and do some actual math. And so Again, when we're looking at the equation for this, the math is going to be using the equation that voltage is equal to current times resistance. So when we're calculating for resistance, we have to say that resistance is equal to voltage divided by current. Our voltage is 0.2 volts. Our current is 13 times 10 to the negative 6 ohms. Therefore, what we're going to get is 15 times 10 to the third ohms. So therefore, answer option A is going to be correct. And with that, it looks like we survived to the end of the passage. That was a pretty dense one. Thanks for joining, and we hope that this walkthrough was helpful in your MCAT journey. If you're looking for more practice resources, you can visit our MCAT question bank or premium content hub for thousands of sample problems. Or, if you want a more personalized approach, our MCAT experts provide one-on-one tutoring, as well as individualized study schedules and test-taking strategies that go a step further than just content review. So check out our website to learn more, or feel free to drop a comment here with any questions you may have. Happy studying!